Okay, hello everyone. This is our presentation about the virtual switch platform for host SDN in the public cloud. It's part of the CS643 cloud computing class for about the article for the author Daniel Firestone. He works at Microsoft. Our presenters are me, Imad, and my partner, Jing Hong. So a quick overview about the agenda of this presentation. First of all, we're going to introduce the virtual filtering platform, the cloud scale vSwitch for host SDN policy in Microsoft Azure. The design achieved our goal of programmability and scalability. Concerns around serviceability, monitoring, and diagnostics. Future areas of investigation including new hardware models of SDN and extending VFP's offload language. First of all, what's Azure? It is a cloud platform that offers many services, infrastructure as a service, platform as a service, software as a service. For the infrastructure as a service, it offers many services like VMs, virtual networks, private clouds, VPNs, and so on. The data services includes SQL database, tables, blob storages, and for the application services, it offers cloud services for like caching, service bus, media, analytics, and some mobile services. So the virtual switch SDN policy, it is a software-defined network controllers that rely on the code as opposed to the network bridges and hardware. Why do we need it? Simply because policy application on the host is more scalable. Switching to Jin Hong.
Okay, next I'm gonna talking about the motivation of the work have done by the author and the team. Okay, the first motivation is provide a programming mode allowing for multiple simultaneous independent network controllers to program network applications. The implementations of OpenFlow and similar MAT model often assume a single distributed network controllers that owns programming the switch. However, this model doesn't fit the cloud development of SDN. So their design that not only allows controllers to independently create and program flow table, but it would enforce good layering and boundary between them. The second motivation is provide a MAT programming model capable of using connections as a base primitive rather than just a packet. So OpenFlow's original MAT model derives historically from programming switch and log ethics, and so assumes that package classification must be stateless due to hardware resources available. However, the controllers require policies for the connection, not just a package. For example, end user often found it more useful to secure the virtual machines using states for access controller list rather than stateless ACLs used in commercial switches. The next motivation is provide a programming model that allows controllers to define their own policy and actions rather than implementing fixed sets of network policies for predefined scenarios. Due to limitation of the MAT model provided by OpenFlow, OpenFlow switches such as OVS has added visualization functionality of set of MAT model. There has a preference that instead to based our functionality on the MAT model, trying to put as much as logic as possible into the controllers while leaving the core data plane in the V switches. This greatly reduces the need to continuously extend the data plane every time the definition of a VNet changes. The fourth motivation is provide a serviceability model allowing for frequent deployments and updates without requiring reboot or interrupting virtual machine connectivity for stateful flows and strong service monitoring. Also, customer will note tolerance of taking downtime for individual virtual machines for updates. This goal was more challenging to achieve with the complex stateful flow model, which is non-trivial to maintain across updates. There has two more motivations. The fifth one is provide a very high packet rate, even with a large number of tables and rules, where extensive casing. So more and more controllers being built and a large number of flow tables need to be deployed, each with many rules. This reduced performance as packets had to traverse each table. The last but not least motivation is to implement an efficient mechanism to offload flow policies to programmable NICs without assuming complex rule processings. Okay, they already have many solutions. One of the solutions is Open-V switches. Linux and Windows support bridging between multiple interfaces, which can be used as a V-switch. This bridge doesn't apply SDN policy. Other public clouds such as Google have described using host SDN policy. Details are not public. So OVS is the primary solution today to provide V-switch-based SDN, and so this is the main comparison point in this paper. However, there have many drawbacks of OVS design. The first drawback is OVS doesn't natively support the two independent multi-controller models as is required when all VL2 and Ananta applications are controlled separately. And also, OVS doesn't natively support stateful actions like NAT in its MAT model, required by all Ananta example. In both cases, controllers need to operate and connections as a base primitive rather than package. The third one is OVS's VTEP schema requires explicit kernel interface to implement VL2 stack VNets, then allowing the controllers to specify its own in-cap and or decap actions, which are not natively supported in OpenFlow. There has two more drawbacks. OVS doesn't support a VL2 stack directory system required to dynamically look up customer address to physical address mappings. And the last drawback is OVS doesn't have a generic offload action language or API that can support combination of policy, such as an Ananta NAT plus a VL2 in cap. Because of all those drawbacks mentioned above for OVS, so a different design is needed for all policy. So the VFP design has three main components. The first one is filtering model. The second one is programming model. The third one is packet processor and flow compiler. Here is the more detail about filter remoter. Filter remoter has two components. The first one is ports and the NICs. The core VFP motor assumes a switch with multiple ports, which are connected to visual NICs. And the second component is Hyper-V switch extensibility. Hyper-V includes a basic V switch to bridge VNICs to a physical NIC, and the switch is extensible, allowing filter to plug in and filter traffic to and from VNICs. VFP acts as a forwarding extension to Hyper-V V switch. So the second part of VFP is programming model. VFP's core programming model is based on a hierarchy of VFP objects that controllers can create and program to specify the SDN policy. The objects are the number one is port, the basic unit that VFP policy filters on. Layers, the stateful flow tables that holds MAT policy. Third, groups, entities to manage and control related groups of the rules within a layer. And the fourth one is rules, the match action table entries themselves. Here is more detail about the layers. So I'm gonna briefly talking about this part. VFP divided a ports policy into layers. Layers are the basic match action tables that controllers use to specify the policy. And also they can be created and managed separately by different controllers, or one controllers can create several layers. And critically, packets traverse layers in the opposite order when inbound than when outbound. Here is more detail about rules. Rules are the entities that perform actions on matching packets in MAT motor. And also there has two parts of rules. The first one is conditions, and the second one is actions. A rule descriptor also has an action. The action contains a tab and a data structure specific to that tab with data needed to perform the rule. Okay, more detail about the groups. Rules on a layer are organized into logic group for management purpose. For visual machines with Docker style containers, each with its own IP groups can be created and managed on a per container basis by setting an IP condition on them. And for stateful firewall, infrastructure ECLs and customer ECLs can be expressed as two groups in a layer. In addition to priority-based matching, individual groups can be longest prefix matching on a condition tab to support routine scenarios. This is implemented as a compressed chair.
Okay, so next is packet processor and flow compiler. As we scale the production, Deployment of VFP and SDN became more widely used. It became necessary to write a new VFP data path for improved performance and scalability across many rules and layers. The goal is to improve performance without losing the flexibility and programmability of a VFP API. Switching model. In addition to SDN filtering, VFP also forwards traffic to ports through these mechanisms. Packet forwarding. VFP implements a simple bridge forwarding packets by destination MAC addresses to the port attached to the VNIC created with that MAC. Next is the hairpinning and mirroring. To accelerate these workloads, we support hairpin rules in VFP layers, which can redirect packets to the VNIC back out through VFP ingress processing, either on the same or different VNIC. Last, the QoS. The VFP supports applying max cap policies on transmit and receive to ports or groups of ports on switch. Operational consideration includes rebootless update. In an update, we first pose the data path and then detach the VFP from the stack, uninstall the VFP, which acts as a loadable kernel driver, install a new VFP, attach it to the stack, and restart the data path, which the whole process takes less than a second. The state save restore. Because we support stateful policies such as ACLs and NAT, a rebootless VFP update by default forces VMs to restart all the TCP connections. Monitoring. Information is continuously uploaded to the central monitoring service, providing dashboards on which we can monitor flow, utilization, drops, connection, restart, and more. Diagnostics. VFP provides a diagnostic for production debugging. Moreover, the hardware offloads and performance. The VFP implements several hardware offloads, which includes stateless tunneling offloads. VFP programs NICs with these offloads for tunneling, which are widely deployed in data centers. Next is the QoS offloads implemented and deployed and interface to offload port level QoS policy to remove the overhead of applying QoS through software. Offloading VFP policy. No packets traverse the host, which is impractical on server NICs, as it often requires large TCAMs and CPU cores. Performance, as we see in the charts, we first see that under a TCP SYN load, the classification algorithm improves by 1 to 2 orders of magnitude over linear match a distribution of random rules. Next, we can see UFT caching improves performance even at 1 layer, but more dramatically as more layers are added. Finally, due to locking in VFP version 1, performance doesn't improve as we scale to 8 CPUs, while UFT scales well. In summary, there has been 2 major motivated examples here in our presentation. The first is the VL2, which can be used to create virtual networks, VNets, on shared hardware using stateless tunneling between hosts. The second is Ananta, a scalable layer 4 load balancer, which scales by running the load balancing NAT in the vSwitch on end hosts, leaving the in-network load balancers stateless and scalable. In conclusion, the author has introduced the VFP, which is a virtual switch platform for host SDN in the public cloud. It is a Microsoft Azure's solution to improve programmability and scalability in cloud distributed system platforms. While the VFP has successfully achieved its goals, the author shows some of the concerns about serviceability, monitoring, and diagnostics. He also showed that the improvements in software has outpaced the improvements of hardware model of SDN. And he finally suggests extending VFP's offload language. That was it for our presentation. Hope we covered the article in all aspects. Thank you for your time.